All right, thanks for the invitation. So this work came about really based on the prior talk, because if some of the surfaces were empty, so I assume that in the prior talk you went beyond Markov, you looked at the Markov level surfaces. And so if the sets were empty, then of course you don't have a theorem. So the question is, when are the sets not empty? So we start off with some general statements. Just defining an affine form. So affine here simply means not homogeneous. And we have an affine form in n variables, and the leading term is f will be denoted with a f naught. And we want the form to satisfy the absolutely reducible condition. For the cubic forms, which is our main topic, the letter will be a capital letter. So whenever you see a capital letter, it's a cubic form. VKF will be the set of integer, the set of points in the set X, and we are mainly interested in the case when X is an integer. And this entry will simply be the number of elements in the set. And of course, the basic question is, when is the set empty or infinite or Zariski dense, which is what we'll focus on today. And so we have this definition, this notion. So we say a set is, so we say a form is perfect if the integer points are Zariski dense for all but finitely many of the case. So we are looking at f is equal to k over z, and so if the set is Zariski dense, so we for all but finitely many k, then we have perfect, almost perfect. I'm sorry?
Did you say what divisible means?
Oh, where is it? Oh, yeah, sorry. In all of these problems, there are local obstructions, and the local obstructions are usually given by a finite number of congruence classes, and admissibles are all the ones that do not have the local obstruction. And in fact, I think, didn't somebody mention admissible today? Didn't you mention admissible today? Almost perfect is the same statement, but in the number of, so
no local obstructions.
Right, no local obstructions. So almost means you look at the set k less than or equal to k, and then k admissible. And it'll be natural density in that set. And full is we remove the Zariski dense condition. So it's almost all, but we don't check for Zariski denseness. And lastly, we have this notion of universal. Universal would be that there are no local obstructions.
Sorry, little v sub f is just the number of integer points?
Yes, number of integer points in the points going to infinity. So you have lots of integer points. We don't check Zariski dense, and it's true for almost all admissible. Okay. And so the question is, given an f, does it satisfy any of these conditions? And more interestingly would be, are there any universal f's? And Voigt's conjectures say that if the degree is too big, then we will not get Zariski dense. And so we will mainly be focusing on the cases when the degree is less than or equal to n, the number of variables. So best to start off with some examples. When n is equal to 2, so binary forms, the quadratics are generically never full. The cubics, and so now for cubics, of course, now you have the degree is higher than the number of variables. So Voigt's conjecture should kick in, but of course these are theorems for these cases, and we have Thuy and Ziegel's theorems. And Schmidt says even more, and that is that there are very few admissible cases for which the integer points set is non-empty. And as mentioned before, Davenport's theorem is that this sum of 4 cubes is full. So full, again, you have infinitely many solutions for each k. and it's an almost all condition rather than a growing number of, yeah. So no, not infinitely many. You have a growing number with k, and it's an almost all k. So that's Davenport 39. Hooley, in a recent paper in 2016, says that for a homogeneous cubic and non-singular, that if you have n is at least 5, so the number of variables is at least 5, then you have fullness. And if you assume the Riemann hypothesis, then you may bring it down to n is bigger than or equal to 4. And the conjecture is that that you have perfection. So perfection, again, remember, perfection means all k except for finitely many and Zariski dense. So way beyond full.
What?
Yes, Hooley's.
Nobody's put it in front before. Ah, that's a very dangerous concept.
Yeah, it's in his paper. So.
No, I don't think that. People know that they try to reduce the variable, but to get down to 4, like, it's a dangerous.
Yeah. Now, for if you have too many variables, then you have the Browning-Heath-Brown result, where n is at least 10, and then you have perfection here. So this is all but finitely many k's. So that's a beautiful result. So as you can see, for cubics, the case n is equal to 3 ternary cubics is the kind of the hard case that is to be discussed. Sums of 3 cubes is, of course, the most famous ternary cubic, and for which, so there are local obstructions. So this is where the admissible ones come in. There are local obstructions if k is congruent to 4 or 5 mod 9. What is known is that when k is 1, then you have Zariski dense, and that is due to a paper by Lehmer in 1956, where he constructed an infinite family of one parametric solution sets. And it's really it's quite beautiful. And strong approximation in the strongest form fails. Meanwhile, if the f factors completely into linear forms, then the number of points is finite.
What do you mean in strongest form?
You want to explain that, Peter?
It means that there is this is due to Castle's developed further by Brown and then made into a theory by Markoff-type. For a given k, there is a modulus q, and it has a Brown-Manian obstruction, relative to which, but it comes from cubic reciprocity, relative to which mod q you won't get all residue classes. So, for example, if k is 3, right at 3 is the sum of 3 cubes. There are solutions, but it's what Castle's observed. So if you write 3 is the sum of 3 cubes, then x1 must be congruent to x2.
X2 must
congruent
be
to x3 mod 9, which is not a local.
Right.
It's not forced locally, but it is the condition demanded globally by reciprocity. So that you can find for every k some progression which is missed. But nobody knows a Haase failure for any possible every number that's not 4, 5, mod 9 is the sum of 3 cubes. And that looks harder than any effect. Mordell in his book says this looks harder than his pi normal number. We have no idea. But nothing is known about something other than that. A weaker form is probably true, and we actually establish it, so that's why it's distinguished.
And for norm forms from a cubic field, you can see that there are very few k's that are represented. This is a series of papers by O'Donnell. So the results in for ternary cubics is very sparse. And of course, the Markov is a ternary cubic. So the question is, what can one do? Well, before we get to that, so let's talk a little bit about perfection. So when do you not have perfection? You don't have perfection if you have infinitely many Haase failures. And so
perfection again is
Perfection is all integers are represented except for finitely many.
Okay.
So you need infinitely, all admissible,
Well,
all
that's
admissible.
The Haase principle is true for essentially all k.
You're right.
But why do you?
And you have Zariski density.
But what is?
Zariski density is
why
a
is there something better than perfect?
well, universal would be all k.
You'll see.
Universal will drop the,
So all, there are no exceptions.
you'll drop the admissible condition. Everyone is admissible.
So universal, perfect, and then
Almost perfect and then full.
okay.
It's a hierarchy.
Okay.
And so Mordell, this is related to the Markov equation, but there's a factor of 2 in there. And he observed that when you choose a certain case, then, so I'm not going to go through all the details here, that you actually get Haase failures, that you don't have any local obstruction, but you have a global obstruction. And the famous Kessel's-Guy's paper, you have a similarly, you have the suitable sums involving cubes. So all of these are not perfect. And there are lots of examples of this type which are not perfect. But if I give you a particular equation, it's of course hard to determine whether it's perfect or not. All right, so the main topic is Markov level surfaces. So we, m of x will be our Markov equation without the factor of 3, by the way. In the original Markov equation, there was a 3 x1, x2, x3. And so we call this the Markov. So V0 will be the original Markov triples. And there are local obstructions. And you can see the local obstructions over there. They represent about 5/12 of the numbers. And gamma is going to be our group of transformations. So there will be the 3 Vieta operations that were mentioned before, plus so because of the structure of m of x, you can see that if you permute the variables, then of course that's in the group. And also if there's another operation, that is if you changed a pair of signs, then you'll still preserve the surface. So the group will be generated by permutations, double sign changes, and the 3 Vieta involutions. And when k is equal to 0, which is the Markov case, the point 333 was the root that was mentioned before. In the previous lecture, it was 111. That was because of the factor of 3 in the Markov equation. And there's only one orbit. And in a paper by Corvage and Zanier, they showed that, it was a remark that V0m is Zariski dense. Now, so there are a series of papers due to Markov, Mordell, Hurwitz, and quite a few other people, and that is that there are always finitely many gamma orbits. And this is the statement, this is descent, what is referred to as descent, when k is not equal to 4. When k is equal to 4, we have the Cayley cubic, and you have infinitely many orbits, and they're generated by those points 2AA.
This is where the Chebyshev polynomials arise?
Is that? I don't think the Chebyshev arise. Oh, yeah, but wait, the Chebyshev arise here, doesn't it?
Yeah, that's
No,
exactly
but
it.
you were operating on the biases there, right?
No. He had the Chebyshevs yesterday.
I think this is where it is, right?
This is it.
Yes, eBay is a variable.
The sign one.
Right.
Yeah.
So always nice to see some pictures.
2 and then 1. K equals 1.
Sure, but there's a...
Well, that's because there's a factor of 3, remember? So that's been adjusted. So this is the case when the surface k is equal to 6. And when k is equal to 6 and above, you always have one component of this type. When k is equal to 4, this is the Cayley cubic, and you have the pinching. And when k is 3, you have this middle zone. Whoops. And then as it decreases, and when k is negative, you always have images of this type, 4 separate components. So the negative case.
What is this dot in the middle?
K is
Well, I'm just pointing out that this keeps shrinking.
Okay, understand.
I did not magnify it, it's just shrinking. And then it disappears, and then when k is negative, it stays in that shape. So the cases when k is negative and k is positive are quite different in the analysis. All right, parametric solutions, which were mentioned yesterday. For the Markov level surfaces, if k is not of the form 4 plus a square, then there are no parametric solutions. While when k is of the form 4 plus a square, then there are these parametric solutions. And the proof of this is, well, I think it's quite cute, because it actually uses the Vieta moves quite strongly. You start off with the polynomial solutions, and then you apply Vieta to them, and you can then create a new polynomial where the degree decays, and in this way you get down to 0, and then it's proved. Zariski denseness, the Korojava-Zanier result extends. If k is not a square, then if the set is not empty, then you have Zariski dense. So that's good, and the argument is really quite similar to what they have done. So I mentioned this, so if you remember in the sums of 3 cubes result of Lemma, you get Zariski dense because there are an infinite one-parameter family of solutions. So for Markov, you cannot show Zariski denseness by using parametric solutions because there are none. So you need a separate argument for Zariski denseness. And so here you definitely have to use the group. In the sums of 3 cubes, there's no group action. So
parametric family of solutions are the solutions which is basically a curve.
Yes. There are integer points on.
Is it obvious that there are no parametric solutions?
For what? For Markov? Well, that's what I'm saying, that you can prove it, that there are no parametric solutions.
Not hard.
It's not hard.
But it's not completely obvious.
No, it's not obvious. You have to use the group to show that it's not possible to have parametric
So
solutions.
that's in your paper.
Yeah. Right. So my point simply is that there are 2 separate things that one has to do, that you cannot use the parametric solutions to create
And there are no
Zariski.
families labeled by 2.
There's no what?
So you can have a parametric family where you
have 2 parameters.
Oh, we didn't check. Right. So once you don't have, yeah.
Some of these have a multi-projection. There's a mass work of the sky and state.
Right.
Maybe that's one.
Right. I think there was some work by Mordell too that had more variables. Okay, so let's go back to some general statements. If you look at something which is a deformation of the Markov, so Markov is sums of 3 squares and then a product of the 3 numbers. So over here we have the product of the 3 numbers, and then the sums of squares is replaced by really a quadratic polynomial plus a linear term plus a constant. And and by choosing the coefficients a, j, j to be plus or minus 1, you still have a nice group action which preserves integer points. So in this way, you can ask if one can create forms for which you get perfection or any of the other theorems that we are looking for. And so here are a couple of examples of forms. So this is Markov plus a linear deformation. This is Markov with a slight quadratic deformation. And for these, you can actually show that they're universal. In other words, this means every integer can be represented. Every but finitely many integers can be represented. And they are Zariski dense. And they have one parameter family of solutions too. And that's just a bonus. So there are these universal forms. However, we do not know of any other ternary universal forms which are not of this type. So it's just in some sense lucky that we got this.
Describe the set of
I'm sorry?
Please, do you understand what the set of things you have to add to the Markov equation to get universality?
Well, I mean, we added them to just make sure that we can get the one parametric family. Yeah. No, right. You can create much more, but.
I mean, a good example would be x1 cubed plus x2 cubed plus 2x3 cubed. That's got no local obstructions at all. So it probably represents every number in the Zariski-Lenz way and with this weaker form of strong approximation. But there's no proof.
We don't know how to prove that, yeah.
But that might be a universal. That might be
x1 cubed plus x2
cubed plus 2x3
2x.
cubed. That has no local obstruction.
Yeah.
So that's adding x3 to Markov.
Yeah. Okay.
I think Mordell has a paper on this equation. Exactly this equation. x1 cubed plus x2 cubed plus.
Oh, it's been studied locally, and then so nothing. That's probably universal. I would guess it's universal, but nothing is known. Nothing. It does not satisfy the very strongest form.
And if you parse to higher degree forms like quaternary forms, are there universal results?
I think get on with you'll get too far afield here. I think in the break you should discuss it.
Okay, Haase failures for the Markov. So M is not perfect, which means that it has infinitely many Haase failures. And this is proved simply by quadratic reciprocity, not cubic, just quadratic reciprocity. And the arguments are quite straightforward, and they are in some sense based on arguments that Mordell had when he looked at similar questions before. It took us a little longer to deduce these things, but certainly for case of this special type. So there's a philosophy here. When k is equal to 4, that's when you have the Cayley cubic. So these are really deformations of the Cayley cubic in mod primes where p divides nu squared. So for the Cayley cubic, of course there are lots of solutions, but by deforming them you can actually show that you do not satisfy quadratic reciprocity.
I mean, what we're trying to understand here is the local to global principle. And this says that you don't have a local to global principle with only finitely many exceptions. That's why.
So this theorem proves, for example, that the number of Haase failures less than equal to x, case absolute value of k is less than equal to x, is larger than square root of x over log x to the 1/4 or something like that, but certainly larger than x to the half minus epsilon. So there are quite a few Haase failures in this situation. Okay.
So it's never obvious. Like if you take sum of 3 cubes, then we don't know how to make Hasse values.
Right.
It's an engineering issue. This a lot of luck behind it.
Okay, so I'd like to talk about descent a little bit. Descent is as old as it comes. I mean, it goes back to Markov and Hurwitz and Mordell, and there hasn't been much done with it. What has happened with descent is you can show that every integer point is equivalent to some finite set, to some points in some finite set. The problem has been that among the points in the finite set, you do not know if they are equivalent or inequivalent. In other words, do you have a minimal finite set? And it turns out that you can actually answer this question, at least in some cases. So to do that, we define this notion of an integer being generic. And generic simply means that we, in the equation, x squared plus y squared plus z squared minus xyz is k. Generic means you avoid case with x is 0 or x is 1 or x is 2. So if the size of one of the variables is 0, 1, or 2, then you avoid those cases. And if you analyze what that means, so of course when x is 0, it means that k must be a sum of 2 squares. So you throw out all the case when k is sum of 2 squares, and so on. And this is the other case. And I only have 2 conditions here because the third condition will be when k is of the form 4 plus a square, which is a sum of 2 squares. So k is generic if it's not one of these. And of course, the number of things that you're throwing out are little o of x things. So you're not throwing out most of the admissible elements. So this might be a 1/4 item. I forgot. So there are about 7 over 12 generics. That's because 5 over 12 were did not satisfy the congruence conditions. And the numbers that you've just thrown out here are little o of k of such elements. So if you consider the generic cases, then you can get this fundamental set, and all the points in the fundamental set are inequivalent. And rather than read through this, it's much better to look at a picture. And the picture is, so here is k is equal to 3, 6, 8, 5. And the green dots are, so 1, 2, 3, 4, 5. There are 6 points in that little triangle. And every other red dot is equivalent to one of the green dots. And none of the green dots are equivalent to themselves. They're inequivalent. So that here we call this the class number. The class number is 6. It's a slightly better picture. So this is the same picture blown up. And you have a close-up of the fundamental set. So this is for positive k. And for negative k, of course, if you remember, the picture will now be different. And the blow-up of the picture is of this type. And there are 9 points in here, and the class number is 9. So this brings up a question of studying how these class numbers change. And we did some computations on those, and we have some minor kind of hopeful conjectures. But I'll come to that in a second. So that is descent.
So is there a Duke theorem?
I'm sorry?
Do the class numbers go to infinity, or do these points have redistributed?
We don't know. We don't know.
But you conject? Okay.
Yeah, we have conjectures.
These are class numbers more like cubic, binary cubic forms. The class numbers are very small. They don't grow.
They have size about logarithm, log squared on average. So they grow very slowly.
I mean, the fact that they grow is the source of all of everything we do. That's Duke's theorem, the class numbers grow like power.
So I'll actually have a few statements on the average size.
We zero entropy.
Right. Okay, so as I mentioned before, in this theorem, there are 2 components to it. One is descent. So descent is classical. And the second component is to show that the points in the triangular region, for example, are inequivalent. So that requires some new idea. And the new idea here is to use a function which keeps track of how the points move as you apply the group operation. And the function we use is this delta, I call the delta function. It's a very simple function, but when we first constructed it, believe it or not, we used a Bhargava cube, this particular Bhargava cube. And why would you even think of using such a Bhargava cube?
What is a Bhargava cube?
Well, let's just call it a cube. So Bhargava's theory for quadratic forms and its cubes. So this is an example of that. So you take a cube and you label the vertices in some way. So here our vertices are labeled in a very special way. All the opposite terms are the same. And there's one term with a factor of 2 in that. Now if you slice this cube in, there are 3 different ways you can slice the cube. Those 3 different ways correspond to the 3 Vieta moves.
Slice, you mean
if you slice it in this way, for example, you'll get two 2 by 2 matrices. And if you compute the determinants of those two 2 by 2 matrices, you will get something that is invariant under the Vieta move.
So slice it by the plane parallel to the sides.
To the sides, yeah.
Okay.
And there are three ways you can do that. And those three will give you the three Vieta move conditions.
Wow.
And if you then take the discriminant of this whole cube, you get this function delta. And the function delta, of course, is not invariant under the Vieta moves. But if you operate...
What do you mean by the discriminant of the cube? Sorry.
The quadratic.
So
It's just a cube. What is the discriminant of the cube?
so if you take this cube and if you slice it, then you will get three different types of quadratic forms, and the discriminant of those quadratic forms are the same for all three slices.
Okay.
And that is the discriminant of the cube.
How explained Gauss's composition using this cube?
Right.
That's cool.
But it turns out that this notion is actually was known before. It's called a hyper-determinant, and this is Cayley's hyper-determinant. And there's a book. And well, I don't want to cause problems here. I'm just telling you what I found.
Cayley is that.
And
I think the moral of the story is if you look at Markov or anybody that does descent, they make some clever function which you make smaller by using the moves.
right.
This is a more refined thing which allowed him to compute, allowed Amit to compute an exact fundamental domain for a nonlinear action which looks like Gauss's fundamental domain. Quite stunning. That's really what's going on. How he found it is another matter.
How did you find it?
Well, like I said, I mean, when I first thought of it was I was thinking of the Vieta moves, and I actually thought that there were three Vieta moves, and if I could construct a cube with determinant, which preserves the Vieta move, then
So this should be Cayley-Ghosh cube.
no, let's not. See, now we are getting carried away. All right, so if you look at the action of a Vieta move on this delta function, then you have this beautiful factorization. And what's beautiful about it is that, so whether it's positive or negative really depends on this term over here. And so remember the notion of generic that we threw out all these points, that guarantees that this is never changing sign. And so by doing that, you can then ask yourself, how do the points move? And it turns out that there are only two possible ways that they can move. You either get movement in this direction, so you get, this is the starting point. You either go 2 up, 1 down, or you go 3 up, from which you can show the uniqueness for the fundamental domain condition. So it's kind of a nice function to use. It turns out that this generalizes to the Hurwitz in 4 variables. And there you don't use a cube, you use a 2 by 2 by 2 by 2 hypercube.
But that's not the homogeneous already, right?
I'm sorry?
That's not the homogeneous already. Like there are more than one function then invariant and
Oh, I know that there's more than one, but
so do you need all of them or
no, just one is enough.
one is enough?
Yeah. If I use the full function, the discriminant, it was so huge that I just gave up on that. But it turns out that if there are two invariants I and J, and if you use I, for example, it works.
Perhaps you should go back to your fundamental domain just to show them how much it looks like Gauss's. Yeah, come on.
Like Gauss's domain for what?
For binary quadratic.
For binary quadratic forms. So
Explain that.
so for the positive case, every point, so let's see. These are the points on the Markov surface, and one of the variables is negative, the other two are positive. And so every point is equivalent to, so if you take a point in this set, so for example, if this was 1, 2, 3, then the corresponding point over here will be minus 1, 2, 3 on the surface.
Let me, in the normal, if you read Gauss,
ABCs.
you have B squared, ABC is the
So
quadratic.
Right.
This could
Then you have,
Right.
you have B less than or equal to A less than or equal to C is Gauss reduced. If
Right.
D is negative. And you have to look at all the solutions where B squared minus 4AC equals D.
Right. So this is the,
Saying you order them, U1 less than or equal to U2 less than or equal to 3, satisfy the equation equals K, and those are reduced forms, and they are inequivalent.
Right.
Exactly. But the action's nonlinear, so it's quite stunning.
But
So-
the fundamental domain looks like the fundamental
So
domain.
show the next picture.
Oh, I see what you mean.
so the triangle is the fundamental set,
I see.
and the integer points in there are the elements which generate all the others, and they are inequivalent.
Wow.
And this is the case when k is negative. There are these 9 points, and they are equivalent. Anyway, but I'm running out of time. I have 10 minutes.
I know how you feel.
All right, so here's some remarks.
I should leave the room.
So H is the class number. H of 46 is 0. That's the first positive Haase failure. The first negative Haase failure is -4. One can prove quite easily that the class number never exceeds k to the 1/3 plus epsilon. And one has an average result that the class number has average size about log squared. So it's quite small on average, but still growing. And this is the remark that Peter was making. The fact that this is growing allows us to prove what we call the main theorem. This is not the main theorem. We haven't gone to that yet.
Can it ever get as large as k to the 1/3?
No, I don't think so. This is a very, very crude result.
I mean, for real quadratics, the average value is 1,
Right.
but there can be as large as root.
It could be, but we have no reason to. We have nothing.
This is more like binary cubic, so it could be like what Lillian did. It would be the subconvex would be beating k to the 1/3
Third.
with some small power.
We have no idea how to.
We conjecture it's k to the epsilon.
Yeah, conjecturing k to the epsilon, but maybe maybe it's
There aren't
wrong.
any
We don't know.
subsequence of k's along which you know it grows.
No, no,
This is
much harder. Okay, so the main result is that M is almost perfect. So again, hard to remember definitions. Almost perfect means Zariski dense. For admissible k, for almost all k which are admissible, you have integer points.
So this is exactly the almost all local developments.
Right. Yes, so this is the analog of your theorem.
Or the analog of Hooly's theorem proved in fewer variables for a special, in this very cubic form, but very special.
Okay, the proof is a variation of the paper of Sarnak that was mentioned earlier, and a paper of Bourgain and Fuchs that was mentioned earlier. In fact, we started off doing the proof by the Bourgain-Fuchs way, and we could get positive proportion, and then we thought perhaps we can do better. So rather than go into technical details, let me just point out some semblance of what's happening. Suppose you look at suppose you look at products of three numbers, and you want to show that there are quite a lot of them. So you fix one of the numbers. So if I put x1 is equal to a, and if you look at x2, x3 is less than or equal to k over a. Now, of course, when you do the Dirichlet argument, you have these tentacles that come into play. And tentacles for us is not a good thing, because we have few theorems that we can use to control these tentacles. So it would be nice if we could just cut off a sector in the middle portion and still win. And of course, in general, you would not expect to win. But if you if you have enough variables, you do see that you can win, because if you choose this sector where each of the variables x2 and x3 are sized approximately the square root of k over a, then the total number of points you will have will be sum over a, k over a. And so now you see that you get a logarithmic term coming in. And so you just win by a tiny amount by preserving the sector. And this is what we are doing over here. We are fixing one of the variables, and then the other two variables, we let them grow in a sector. So this argument really makes full use of the shape of the Markov equation, something that you obviously don't have in your more general setting. And so this is the main reason that we win. So to do this, we let R A of k be the counting function within this sector, and the B A k would be the sum that we are looking for as you sum over all the a's. And we look at this variance function. So in this variance function, there are some parameters. The little a is going over a range capital A, and the BAK is counting the number of points. And this is what you would expect the count to be if you just look at the main terms that come about. So delta m sub k over here is the density function.
What is capital A that's not calligraphic? Log A?
Capital A is simply, so the size of calligraphic A is capital A. And how big is capital A? So for us to analyze this sum, we need to show that this sum is small. In other words, little o of k. So to analyze this sum and show that this sum is little o of k, we have to use these theorems of Blomer and Granville on quadratic forms, distribution of values of quadratic forms. And those theorems, by the way, are for definite quadratic forms. So our forms are indefinite. So we couldn't quite use those theorems. However, by a little trick, we were able to use those theorems. But the theorems have a restriction, and the restriction is that the discriminant of the forms cannot be too big. And so that restriction on the discriminant tells you how big the A to be taken. And A is going to be about the size log of k. So we are really going into the log-log zone here. But the point is still going to infinity. So again, I think it's quite similar to what you were talking about earlier, where with your y, where you cut off at y. So we have a similar kind of analysis here. So the circle method comes into play. This is a circle method which has 4 variables in it. I really have 2 or 3 minutes, so I'm going to zoom right through now. Okay, so let's go to some computations. So here we counted some Haase failures, and I hope you can see. So here are the case, the interval. So by the way, these are only for the positive case. I did not do any computation for negatives. So here's the interval capital K, the number of Haase failures in the interval. We have a guess as to what it might be, and if you look at the guess, well, even when I looked at the guess, I was a little surprised as to how good it was.
The guess is based on product of local densities. You just
right.
You said that.
No, I didn't say that, but that's because we were guessing the product of local densities
So
too.
you just kind of assume that the product of local densities gives you the count of the number of solutions. If it were bounded, this would be very unlikely it would work. That's the fact that it's growing like a log means maybe it's going to try to be better and better as scale gets large, and that's a remarkable thing with the variance.
So it appears that the number of Haase failures actually grows like a power of k smaller than 1. We don't know what that number might be. So none of these computations, I can't have too much confidence in these computations because remember, these functions are growing so slowly. And even with k as large as 10 to the 7, by the time I did the computations, it took months. It just takes a long time to get these things done. So so then we looked at Haase failures in sub-intervals. So we took intervals of length 100,000, and we counted how many Haase failures there were. And this is the proportion of Haase failures in those intervals. And you can see a very nice kind of distribution. And so what this oops, I'm sorry. What this tells you is that I'm sorry, this is the distribution for the Haase failures in short intervals, and the dark curve is given by this, so it's a decay. The decay is again still a power of x. So we are still going down by a power of x. Okay, so here are some examples of, these are just some examples of class numbers. And so you can see that the class number equal to 1 comes up quite often. But it's hard to form any conjectures from here. So then we did some computation on how often do class numbers occur. So the left table is the value of the class number. 0 is when the Haase failure, and so on. And then the number of occurrences. And here are the ratio of one occurrence to the other. And you can see that they kind of stabilize. And if you graph it, you get this graph for, so this is the number of class numbers equal to h divided by the number of class numbers equal to 0. And it goes down like an exponential with the square root of h. So if you remember that on average, h was about log squared. And so this is fitting in quite nicely with that average. But again, the surprising thing is for such a small k, it's such a good fit. So maybe one can prove some theorems, but we certainly don't know how to. So conjectures.
H looks unbounded.
What?
H looks unbounded.
Yeah, it looked unbounded. Yeah.
Almost all h.
Right. So our conjectures would be that the class number is bounded by k to the epsilon, and more generally, the number of Haase failures would be about k to some power, and also the number of solutions to h of k is equal to a constant should be about the same power, k to the theta, times some function in t. Okay. I'm 1 minute over, but let me just tell you about, this is the Hurwitz case where the cube is replaced by the hypercube. And if you compute the hyper-determinant of this guy, well, actually, I don't compute that. Like I said before, I use the I, there are two. So you get binary quartic forms, and there are two invariants, the I and the J. And if you use the I form, then you can actually get fundamental sets for this case too. But there are many open questions relating here.
Do you have like a good explanation why these invariants behave nicely under the evolution?
Yes.
Like you had some intuition for that, I guess.
Yeah, I now know roughly what's happening. So, but it might be, it might. So the question that I'm really wondering right now is, if you start off with a structure, can you go backward? In other words, can you create the surface from the this is very symmetric. If you look at the z value over here, they are opposite, but in the opposite cube. So there's a symmetry to it that might actually be more general. And so if you go backwards, then you might actually create the surface rather than the other way around. Anyway, thank you. I'm 2 minutes over.